My name is Cameron Stevens. I am a senior environmental studies major at Alma College. I worked alongside Isabella Centurion, who I would like to thank, as well as Dr. Amanda Harwood. Our research was performed on factors affecting road salt toxicity to Hyalella azteca. When looking into this project, we asked ourselves, why do we care? Why is this even relevant? Here in Michigan and throughout the Midwest, we know the roads are awful in the winter. The first line of defense is putting salt down. In the 2013-2014 season, Michigan put down 653,000 tons of road salt. For us, we wanted to explore how much is put down in just our surrounding area. Alma College in 2018-2019 sent out this email saying they used 14 tons on campus in 2 days. This year, they continue to put down lots of salt over the course of the season. When we received this email, the snow had melted in large quantities already. And this is what drove us to do this project. Road salts have the potential to impact aquatic life as it runs off into the freshwater systems. It's toxic to macroinvertebrates and has negative impacts on the ecosystem. Our test species was Hyalella azteca. They are the standard EPA test species because they're easy to culture in a lab and they reproduce quite quickly. They have an important ecological role in nutrient cycling, and they're the bottom of the food chain, so they serve as a food source for many organisms. And they're also great indicators of pollution. In a previous study by Hunter Wilson and Logan St. John, they performed toxicity tests on 3 different species of macroinvertebrates with sodium chloride and 2 sodium chloride-based road salts. They found that LC50, the concentration that causes 50% mortality, for Hyalella over a 24-hour and a 96-hour exposure. They found that while there is a difference between 24 hours and 96 hours, there is no difference between the sodium chloride and the 2 sodium chloride-based road salts in the 96-hour test. So we were able just to move on using sodium chloride for further testing. So we know that the most sensitive species of the previous study is Hyalella azteca. We also know there is no difference in toxicity between the sodium chloride and the sodium chloride-based road salts. In a project my partner Isabella did last year, she used normalization for chloride ion to show that the sodium chloride-based road salts are mostly sodium chloride. This is important because the chloride ion concentration is what's measured in the environment and what's used to estimate toxicity. Based on this, chloride ion concentration can be used to estimate the toxicity. What we still don't know from the study is whether adults are less sensitive than juveniles. Juveniles are the standard age, but in our study we used adults because that's the age they are in winter, and that's the time when road salt is put down. We also don't know if temperature affects toxicity. Logan and Hunter did their test at the standard temperature, but winter is when road salt is put down, so it is colder than the standard. We also don't know if the LC50s found for the 96-hour test reflect environmental conditions. Concentration in the environment isn't constant, and in the environment, the Hyalella are exposed for longer periods of time. We know there is a difference between the toxicity of sodium chloride and potassium chloride, but we did not know if the exposure type, the duration, or the temperature would impact the salts in any way. Sodium chloride and potassium chloride are the 2 most common salts in road salts, sodium chloride being the most common and potassium chloride being a close second. And we wanted to know if chloride ion is able to be used to predict toxicity when there are multiple salts present. The main objective of this study was to examine more environmentally relevant conditions. The first variable we looked at was temperatures that mimic the environment when road salt application is relevant. Dilution was used to mimic the natural occurrence of salts being flushed from the water. For durations, we wanted to know the effects after an exposure of 96 hours like they would be in real life. We had to keep in mind that not all road salts are sodium chloride based. Number 2 for road salt use is potassium chloride. We wanted to know the difference between these two. And if there was a mix of salts, can we still use chloride ion to predict toxicity? We followed general methods of a toxicity test using Hyalella azteca. With 5 dosing concentrations, 10 adults in each beaker, along with a screen. After exposure, we counted how many were alive. For the colder test, we acclimated the Hyalella to ensure no shock was to happen. We then measured chloride ion at the start and end of 96 hours and after every water change in the 11-day test. We calculated the LC50s for each experiment and concentration of salt and concentration of chloride ion. We calculated this by using trapped EPA software and compared by overlapping confidence interval, giving us a dose response curve. We did 12 experiments in this project. We did 3 exposure types, 96 hours with a 7-day dilution, and then a 10-day constant exposure. For each exposure type, we repeated them at 23 degrees and 12 degrees Celsius. Then we repeated this with the 2 salts, sodium chloride and potassium chloride. Moderately hard water is the standard solution we use for cultures that reflects water in the environment. This video demonstrates how we did our water changes by a pour-over method and screening to protect and capture escapees. For pulse dilutions, we had to do a complete water change, so we did the pour-over method to prevent any shock. The pour-out method is what we are using for the 10-day test since we are only doing a 50% water change, and it prevents less escapees from what we have found. This figure shows the dilution of a sodium chloride solution over 3 water changes in our pulse dilution test. Each concentration is shown by color with percent of initial concentration on the y-axis and the number of water changes on the x-axis. As you can see, it dramatically decreases. It shows that it's important when chloride concentration is measured, the chloride can change within hours in the environment. Even after 3 100% water changes, it goes down to about 10% of the initial, not back to normal. So our first question was, what were the effects of exposure types? On our x-axis is our exposure types, 96 hours acute, 11-day dilution, and 10-day chronic. On our y-axis is the axis LC50 in grams per liter. The error bars are 1 standard deviation. This graph is the LC50s for sodium chloride. There is no significant effect of exposure type on toxicity. And if you remember Hunter and Logan's data, there's no difference between juveniles and adults within a 96-hour period. And here you see the data for potassium chloride. And again, there is no significant effect of exposure type on toxicity. And once more, temperature does not affect toxicity. The next question we wanted to answer is, what about the difference between the 2 salts, sodium chloride and potassium chloride? We also compare the sodium chloride and potassium chloride LC50s. Since there's no difference among temperature or duration, we use the standard 96-hour 23 degrees test. There is a difference between the toxicity of the 2 different salts. Potassium chloride is more toxic than sodium chloride, which brings up the question of whether we can use chloride ion to predict the toxicity. In this figure, it compares the LC50s of sodium chloride and potassium chloride in chloride ion concentration. Chloride ion concentration is what's used to estimate toxicity in the environment. However, since there is a significant difference in the LC50s for sodium chloride and potassium chloride in chloride ions, chloride ion alone may not be a good indicator of toxicity, as it depends on where the chloride ion came from. For an example, if the chloride ion concentration is about 2,500 milligrams per liter, it's well below the LC50 of sodium chloride, but it is not if it came from potassium chloride. If there's a mix of salts, The chloride ion cannot be used to predict the toxicity. Overall, through these tests, we found there was no difference between temperatures for any duration. There was no difference between exposure types. If it was 4 days or 10 days, it makes no difference even with a dilution. And we know now that we can't use only chloride to determine water toxicity. We use chloride levels to determine safe concentrations of salt in the environment, but it depends on where it comes from directly. In the future, we plan to finish our 10-day test with sodium chloride at 12 degrees Celsius. We would also like to do a shorter pulse, like pulsing the invertebrates for 6 hours or 10 hours instead of 96 hours. And we would like to do a temperature that represents a true winter, as well as doing different salt mixtures, such as having both potassium chloride and sodium chloride in the solution. I would like to thank the Alma College Environmental Studies program, as well as Hunter Wilson, who was the lab manager at the time. We would like to thank the CORE program, where we started this project, and thank you to the support from the Costable Endowment, as well as Stan and Louise, our lovely environmental chambers. I would be happy to accept any questions at this time.